name is Antoine Richermoz, and we're going to be talking about voxels. So, what makes voxels an interesting rendering primitive? Well, first of all, since your geometry is encoded as a texture, anti-aliasing just becomes texture interpolation, so simple and fast. They also have well-defined LODs. Meshes LODs can be a real headache, especially for aggregate objects like trees, where they can really fall apart. On the other hand, voxel LODs are just downscale version of your images, so really simple and elegant. So they're just like 3D bitmaps. And finally, because of their very ordered structure, voxels are easy to ray trace using a form of ray marching. So if voxels are so great, why aren't they used more? Well, they have tremendous memory requirements if you use just a simple dense grid. We want to be able to have gigantic roles with high level of detail, pixel-sized voxels, all of that in real time, but there's no way that we could fit a single voxel level stored as a dense grid on a GPU memory. Locally, we don't need to store the whole level, we only need to store what is visible. So if we look at a typical scene here, well, first of all, most of it is empty, it's just air between objects. We also have lots of space that is taken by voxels that are inside objects, that is never visible. We don't need that either. And we also have everything that is out of the view frustum, and everything that is occluded. So we only have a tiny portion of what we started with that is actually needed in GPU memory. And in fact, if our scene is composed mostly of opaque objects, we shouldn't need more voxels in VRAM than pixels on screen, which is much more reasonable. So how are we going to achieve our goal of storing only what is visible? Let's start with the stuff that is either empty or inside, so sparse compression. For this, we rely on a smart data structure. The most commonly one are sparse voxel or trees. They can be really compact, but are quite expensive to access because you have to do a lot of pointer chasing to access the leaves. So instead, for our paper, we chose to use indirection clip maps. Clip map is similar to a bitmap, but instead of each level representing the same area at different resolution, the levels all have the same resolution, but represent larger and larger areas, which is what we want for LODs. And yeah, clip maps are centered around the camera, so you need to update them when the camera moves. But we don't store our voxels directly in the clip map. We only use it as an indirection into a brick atlas, a brick just being a small chunk of voxels, typically 8 by 8 by 8. And that way, we don't have to store empty bricks. And so indirection clip maps are much faster to access because they only have one indirection, but much more wasteful in terms of memory. And there is also a nice poster comparing different voxel data structures. So if you want more information on this, you can look it up. And now for the harder part of what we want to avoid to store in VRAM, which is frustum and occlusion culling. For that, we can take a look at our predecessor, which was GigaVoxel by Croissant and colleagues. It was quite an original scheme called ray-guided production and LA recaching. So it viewed the voxel data structure as a form of cache to store the viewed voxels. And the decision of what to put in cache is made at render time during the ray marching itself. So you have two tasks, the render, the ray marcher, and what we call production, which is creating voxels and putting them in the cache. And the production is triggered by the ray marcher, and when production finished, the ray marcher can continue. So here's how the ray marching loop looks like. So at every step, we check the brick state. If it is in cache, we just sample it and step on. If it is empty, we skip it. And if it is absent, we request its production. And production can mean lots of things, from disk loading to procedural generation, or really anything that can generate voxels. So we have two tasks, render and production. Both of them can be done in parallel. but they operate on different domains, one on screen space tile and the other on bricks. So it is not that straightforward to map on a SEMD machine like GPU. And so here is how GigaVoxel works. It starts by rendering every pixel, start by tracing, recording missing bricks along the way, and when all ray tracing threads are finished, production of the missing voxels can start, and similarly, when production voxels finished, ray tracing can resume. And you alternate between those two steps until the image is complete. So as you can see, there is lots of synchronization points with this algorithm, which can lead to lots of GPU starvation. To better analyze this, we developed a custom tool that we call the GPU core timeline. What you see here represents a single frame of rendering with time on the vertical axis, GPU cores on the horizontal axis, and red meaning that a core is doing ray tracing, blue that it is doing production, and black nothing. And so you can see that we have starvation at the end of each job, and that we have a big section with lots of tiny jobs that we call detail, and this section is really inefficient. For those that might be interested, here is how our GPU core timeline is implemented. All it required is a global GPU timer, GPU core ID, and the ability to instrument your shaders. At the beginning of a shader, it allocates a timeline entry, records to it the shader type, core ID, and start time. And then at the end of shader, it records the end time, so it gives us an interval. And now at the end of the frame, another shader can parse all those timeline entries and create the displays that you see here. And it runs in real time. And so now that we know that our issue is one of starvation, how are we going to solve it? We propose to use dynamic parallelism. Dynamic parallelism is the ability to launch GPU jobs from the GPU itself, something that normally only the CPU can do. So it is particularly useful for workloads that are both dynamic and irregular. As you can imagine, it's quite a powerful feature, but it hasn't really been used much in the graphic community. Perhaps one of the reasons for that is its poor availability. On the compute side of things, on the CUDA and OpenCL, it's really straightforward to use. You can use the exact same syntax to launch kernels from the GPU as you would launch kernels from the CPU. But sadly, on the graphics API side of things, we don't have that luxury. Nonetheless, we can use persistent threads to fetch and put work on a work queue, so making our own scheduler in a way. And this approach seems to be used more and more. It was, for example, featured in Neyret, and it was also showcased yesterday with the HPLock presentation. And interestingly, the mesh shading pipeline also introduced a very limited form of dynamic parallelism, with the task shader being able to launch a variable number of mesh shaders, but you only get one level of expansion, so it's very limited. And so if we apply dynamic parallelism to gigavoxels, we can get rid of all those synchronization points. And now voxel production can start as soon as a ray needs it. And similarly, as soon as the production is finished, ray tracing can resume. So, but of course, there is no free lunch. And with more concurrency comes more headaches, namely data races. So we have a possibility here for two rays to start the same production, and also here for two production to resume the same ray. And those can be solved by carefully using atomic operation. And I refer you to the paper for more information on this. So, and also with our new scheme, we have to think about how to know which rays to resume when a production has finished. With gigavoxels, they could just use a full screen pass, but we cannot do that. So we tried lots of schemes using a memorization, trying to record which rays were waiting for which bricks, but it wasn't really working, so in the end we just decided to try to relaunch all the ways that are covered by the B-box, the screen space B-box of the brick, and it worked much better. So if we compare the diagram, we can see that hopefully we should have much shorter frame times. And indeed, if we look at our timeline comparison, we were able to approximately double the performance. So we were able to eliminate the end-of-job starvation and really scratch down the tail. And you can even see that there is some purple, which means that the same core is doing ray tracing and production at the same time, which is possible because of hyperthreading. And in absolute term, we get about 40 to 90 FPS on a RTX 4080 at a resolution of 1500 by 1000. So it's real time. And now I can do a short demo. If YouTube's want to. Yeah, okay. Can have the resolution. Okay, well, maybe 1080p was hopeful. Yeah. So, on the right, what you will soon be able to see is a real-time view of our GPU timeline. Yeah, okay. And you can see that there is lots of gaps, lots of starvation. It was working before. Yeah. Well, you can find the video either online or it is linked with the article. May I ask everyone to get off the Wi-Fi, please? Well, so what you are supposed to see in this video is similar to what you saw before the timeline, just in real time. After that, it should switch to the dynamic parallelism version, and you can see that the timeline is much shorter. There was also nice debug views showing bricks and voxels. But yeah. Yeah, this is a view of the voxels. Each color is a different voxels, and here compression is not doing it justice, but we achieved our goal of 1 voxel per pixel. And lastly, I will try to show you the cache updating. Well, I do the conclusion slide, and then I'll try to wait for the video to load while we answer questions. So the conclusion, limitations and future work. For limitation, we were able to greatly reduce the frame time, but they are still really inconsistent, which is not great, really spiky frame time, as you can see here. Also, we used CUDA for the dynamic parallelism, and it required a full gigabyte for its data structures, which is not great. Also, because of our brick B-box rasterization technique, we can only do primary rays, so it is limiting. And lastly, we used procedural generation for voxel production, but it is not clear how we could apply disk loading with dynamic parallelism, as currently we don't have any way to initiate disk loading from the GPU itself. And for future work, we would like to try to do a custom dynamic parallelism implementation using persistent threads. Maybe also try to look at cache prediction to smooth out frame times. And lastly, we would like to develop our GPU course timeline tool and make it portable and available for everyone. So thank you for your time, and I'm now ready for questions.
Questions for Antoine?
Yeah, so the question is, if I understood correctly, what is the difference between dynamic parallelism and word graph, or could you apply word graph to this problem? Yeah. From what I understand, word graphs are not able to be as dynamic as dynamic parallelism. You need to declare in advance what path it's going to take, but for us, the graph can be really deep and really dynamic. We don't know which way is going to need which brick. I'm not sure if it is possible to use word graph. I tried to use CUDA word graph, but it wasn't really working. Yeah, I will look more into other word graph APIs. Maybe there is something to do here.
Have you thought of extending this to volume path tracing, maybe Woodcock sampling or something like that?
It is a form of volume path tracing because voxels can be semi-transparent. What was the second part of your question?
Something like real path tracing, where it's not just breakcasting through the volume, but actually doing Woodcock tracking or something similar.
I'm not familiar with the Woodcock tracking.
Okay.
Sorry.
No problem.
So I have a question. So is this dynamic parallelism, is there a way to spread this across multiple GPUs, since this is GPU eccentric? So can you scale beyond a single GPU?
I don't believe that the current APIs allow us to do that. Our goal is to do real-time rendering, which usually doesn't work well with multiple GPUs, or it seemed to have been a bit abandoned the last years. So I'm not sure, but maybe you thought about one GPU doing ray tracing and the other doing production. Yeah, haven't looked into that.
Any other questions from the audience? Let's thank our speaker again.
Thank you.